Welcome to third lecture on advanced computer architecture. I hope you remember in the last lecture we discussed the instruction set architecture. We discussed the addressing modes, and then finally we came up to the point where we discussed two strategies, the RISC and CISC. RISC is basically the reduced instruction set computer, and CISC is the complex instruction set computer. In RISC, as you are aware by now, that the features are, we have a fixed length of each instruction. So every instruction occupies the same number of bytes. Secondly, each instruction is executed in one clock cycle. Finally, in a RISC architecture, all the addressing modes are not supported. That means a simplicity in the addressing modes would result in speed. So therefore, we have a simpler instruction set and expect to gain speed in the case of a RISC architecture. On the other hand, in the case of CISC architecture, we have complex instruction set whereby the length of different instruction sets could be different in number of bytes. As a result, the earlier architectures were usually supporting the CISC architecture. The present-day architectures revolve around primarily the RISC strategy. Today, we'll continue and look into the performance of different architectures. Performance could be measured by different parameters. You can imagine when you are sitting on a computer and you start your program and it takes a long time to execute, you will not be happy with that computer. You would definitely like to have speed. The speed would depend on a number of parameters. The first one, which everyone can imagine, is the clock. If you have a computer with a CPU of 200 megahertz, on the other hand, if you have another computer with 1 gigahertz clock, definitely the 1 gigahertz clock computer would run the same program much faster than one which is with 200 megahertz. However, you can just imagine that clock is not the only parameter. The hardware engineers have already tried to optimize, and we can gain speed in terms of clock. The other parameters could be, for example, when you have defined an instruction set and you want to implement on a particular architecture, then you would see the complexity and see the cost of implementation. However, we will not discuss today the cost of implementation. That could be looked into later on. We just want to see how a particular machine would perform. To check the performance of a particular program, we would define and see some benchmark programs. These benchmark programs would try to simulate the workload of an actual program. So when you want to run the actual program, you would like that this benchmark also has all the capabilities, different instructions which you are going to use practically are implemented in this particular case. So therefore, the benchmark program would give you finally the execution time. So the parameter which would be looked into is the execution time. Smaller the execution time for a given program, faster would be the computer, faster would be the CPU. The execution time would further in turn depend on the processor speed and memory management and many other factors. Some of these factors are usually neglected and are not taken into account. For example, the fetching from the memory, the execution of and storage of the data into the memory is not taken into account in the first case. One could write the execution time in a very simple way as a product of three parameters: IC, CPI, and T. IC is the instruction count, which gives the total number of instructions in the program which one is running. Secondly, CPI is the system clock cycles per instruction. CPI multiplied with the clock time T would represent the total time on the average spent on one instruction, which multiplied with the total instruction count would give us the total execution time which would be spent on executing a particular program of the user. Naturally, when T is small, then the execution time would be small, and a larger time would mean a larger execution time. So this is the system clock. System clock time could not be reduced beyond certain limit. On the other hand, then larger the count in a particular program, then larger would be the execution time. Let us look at an example. In this table, the two programs are given. Program 1 has a total instruction count of 6, whereas the second program has an instruction count of 7. However, this is one parameter. Instruction count is not the only parameter which would determine the total execution time. Let us see the individual instructions. They will need different number of clocks to execute the instruction. So in first program, the number of instructions which belong to ALSU are 2. Similarly, the control instructions are 2, and the data acquisition also is with 2 instructions, whereas we have in the second program 5 control instructions. So in the next slide, you just see the working for execution time using the same mathematical formula, IC multiplied with CPI into T. We see that the total number of instructions in program 1 are 6, whereas the instruction count in the second case is 7. Now, how much number of clocks are required to execute each type of instruction, that is control, ALSU, or data transfer? This would be specified by the designer of that particular processor. In this example, in both programs, we assume that the control instruction requires 2 clocks per instruction, whereas ALSU requires 3 and a data transfer instruction requires 4 clocks. Based on this data, the execution time for the first program is 18 clock units, 18 times T, T is common, whereas for the second it is 17 clocks. Now we see that even though the count for the second program is higher, still the execution time is lower in that case. As a conclusion, we see that instruction count is not the only parameter. It depends what type of instructions are being executed. So even though the instruction count is higher, still we could have a lower value of execution time, as it is illustrated in the last slide that program 2 has a higher instruction count, still the execution time is lower. Finally, the clock period time T, that has to be lower. If we are comparing two different machines, then the one having a smaller value of T would be having a lower execution time and would outperform the other one. As you see on the screen, there are two programs for a sample RISC computer. There are two code segments for implementing multiplication. Program 1 implements multiplication by using repeated addition in a for loop, whereas program 2 implements multiplication using a subroutine call. Let us find out which one of these two programs is more efficient in terms of instruction count and execution time. This table indicates the number of instructions and the instruction count for the two programs. For program 1, there are 7 data transfer instructions, whereas in program 2, we have 6 data transfer instructions. The control instructions are 2 in program 1, whereas we have 3 control instructions in second program. The ALSU instructions are 3 in each case. Now, looking at the total instruction count, you will see it is 12 in each case. So, although the total number of instructions are 12, let us look at the execution time. The execution time from the data of this processor, one could see that control instruction requires 2 clock cycles per instruction, the ALSU requires 3, and a data transfer instruction requires 4. Using this data, the execution time for the first program is 41, whereas it is 39 in the second case. Now, this 39 and 41 is arbitrary, and one could assume that the multiplying factor is the same in the two cases, assuming that the clock is running at the same speed. So, one concludes that although the instruction count for both programs is the same, program 2 runs faster than program 1 due to lesser number of clock cycles required for execution. Execution time is not the only measure of performance. There are other matrices which are also used. Some of these are like MIPS, which stands for millions of instructions executed per second, or it could be another measure which is MFlops, which stands for the millions of floating point operations executed. Then another parameter could be drystone, or millions of drystone instructions executed, or whetstone, and finally the spec. We will discuss these parameters of performance one by one. Let us have a look on the next slide. MIPS is a metric which has been quite often used, and it is millions of instructions per second. If one knows the instruction count, the MIP parameter would be just equal to the instruction count divided by the execution time into 10 raised power 6. the capability of different instructions varies from machine to machine. For example, RISC machines have simpler instructions, so the same job will require more instructions. Now, this index was quite popular when the VEX series of machines were primarily used, and VEX 11780 was treated as a reference. This was so in late 70s and early 80s. MIPS is inversely proportional to execution time. MIPS is not a very good measure of performance. It could sometimes be misleading. When we are comparing two different instruction sets, then the type of instructions could be different. For example, in RISC, the number of instructions could be much higher, and that could not necessarily mean a higher performance. We could have different machines, and one with a higher MIPS would not always mean a better performance. Let us have a look on an example in our next slide. Consider a machine having a 100 megahertz clock and 3 instruction types with following parameters. Now, suppose that two different compilers generate code for the same program. The instruction count for each is given as follows. The number of instructions in millions for code 1 from compiler 1, for example, is 5 for control instructions, 1 for ALSU, and 1 for data transfer. Whereas in the case of code from compiler 2, the number of control instructions are 10 million, ALSU 1, and data transfer 1. So if we compare the two codes according to MIPS and according to execution time, first we find the CPI for both code sequences. The CPI for the first code as calculated would be 5 multiplied by 2 plus 1 multiplied by 3 plus 1 multiplied by 4, and since the total instruction count is 7, we divide it by 7, and this gives us an average CPI for the first program as 2.43. Similarly, the CPI for the second program turns out to be 2.25 million. And the MIPS for the first program turns out to be 100 into 10 raised power 6 divided by 2.43 into 10 raised power 6, which is 41.15. Similarly, if we calculate the MIPS for program 2, it turns out to be 44.44. Hence, the code generated by compiler 2 has higher MIPS rating. Since ET, the execution time, is inversely proportional to MIPS. In the first case, the first program requires an execution time of 0.17 second, whereas the time of execution for the second is 0.27 second. Hence, code sequence 1 is much more efficient in terms of execution time. As a conclusion, we see that although the MIPS rating of the code generated by second compiler is higher, still the execution time of the first program turns out to be better. Now, MIPS is not an absolute matrix. We see that a higher MIPS does not necessarily mean a better performance. Now, the next parameter of performance is the MFlops, which stands for the millions of floating point operations per second. Using floating point operations makes more sense to some compared to using just any instruction. Results vary from floating point operation to floating point operation. It is a better matrix as compared to MIPS because of two reasons. The floating point operations are usually complex and therefore provide a better picture of the hardware capabilities on which these programs run. Secondly, the overheads, that is, getting operands, storing the results, etc., are effectively lumped with the floating point operations these are supporting. However, MFlop index is also not an absolute one. It has its own problems. When we are comparing two different programs based on MFlops, one program might have more complex floating point operations than the other one, and it may not be an absolute measure of performance. Secondly, when we are comparing two different CPUs, two different processors, then in that case, one processor might have more complex floating point instructions, whereas the other one might have simpler floating point instructions. The floating point instructions for different operations like divide could also take more time, and then it could make megaflop also as a ridiculous measure in certain cases. On the other hand, people have tried to modify and get more rational MFlop measures. This could be a normalized MFlop instead of an absolute MFlop, trying to come on an average figure of MFlops. The next measure of performance is a whetstone. Whetstone, by the way, is a place in England, and it was a benchmark program which was developed, a small program having 10 different modules, which is a mix of different types of instructions. Initially, this benchmark program was named after Whetstone Algol compiler. Later, it was also ported for Pascal, Fortran, and C. The result of the benchmark program are reported in terms of the number of Whetstone instructions executed per second, or a figure in terms of millions of Whetstone instructions per second. Based on the 10 modules and a mix of different forms of instructions, including the trigonometric functions and other type of instructions, one could think as a parameter of performance. Let us look at the next parameter of performance, which is the drystone. Drystone is a general integer performance benchmark test originally developed by Reinhold and Weicker in 1984. It's a small program, less than 100 higher level language statements. It compiles to about 1 to 1.5 kilobyte of code. Like other benchmark programs, the drystone measure gives the drystone instructions executed per second. It does not include floating point operations. It is heavily dependent on the hardware, and then it would be not an absolute measure of performance for the computer. It would depend on the individual type of instructions used in the integer mode. Let us look at some of the drawbacks of the drystone benchmark program in the next slide. Both whetstone and drystone benchmark programs are now considered obsolete because of the following reasons. It is a small program which fits in cache, and as such the memory interaction is not included. It has obsolete instruction mix. It is prone to compiler tricks. A compiler designer could give a performance which is fictitious. It's difficult to reproduce. The results are not consistent, and we do not have a unique source code. The next standard for measuring the performance is spec, which stands for System Performance Evaluation Cooperative. Spec was founded in 1988 by a group of companies including Hewlett-Packard, Apollo, MIPS Computer Systems, and Sun Microsystems. It has got different versions. The latest version is Spec CPU 2000. The standard spec benchmark suite includes a compiler, a Boolean minimization program, a spreadsheet program, and a number of other programs that include the mathematical functions and the processing functions. It uses a simple metric, that is the elapsed time, to measure performance of competing machines. Machine-independent code is used for fair comparison. The spec benchmark program measures the execution time for a given suite of programs and compares it with a reference machine like AlphaDec or AVEX. As a ratio, it would give a dimensionless figure. It would also be independent of the program length and would be able to compare different machines in a more appropriate and reasonable fashion. As such, spec, out of all the measures and the matrices which we have discussed, is one of the better ones and is used at present. The spec measure has a number of advantages. It provides ease of publication. When comparison is to be made for different applications, then spec could be specified and it would be quite a good measure of performance. Each benchmark carries the same weight. The spec ratio is dimensionless. It is not unduly influenced by long-running programs. It is relatively immune to performance variation on individual benchmarks. In general, it provides a consistent and a fair, unbiased metric. To summarize, we have discussed a number of measures for performance of different architectures of CPUs or computers. We discussed the time for execution. We discussed the measure in terms of MIPS, in terms of megaflops, in terms of whetstone and drystone, and finally the spec. As a conclusion, the drystone and whetstone are obsolete. The MIPS and MFlops could give a misleading figure, and spec is quite a fair and unbiased measure of performance. After talking about the performance measures, let us turn our attention to a simple processor which we call SRC. In the textbook, it is named as Simple RISC Computer. It is a simple general purpose register machine. Although it is simple, but still it is quite close to the real machines to illustrate different design concepts. We would like to look at the ISA of SRC. But before we discuss the actual ISA, the actual instructions, let us see what are the features of this SRC. Basically, SRC has 32 general purpose registers. Each register has 32 bits. There are two other registers, special registers, the program counter PC and the instruction register IR. The memory word size is 32 bits. The total memory is 2 raised to power 32 bytes. The memory is organized in the form of bytes, so we have a total addressable space of 2 raised to power 32 into 8. The word is organized in the form of 4 bytes, that is 32 bits. So whenever we fetch data from memory into CPU, it would be in chunks of 4 bytes. The convention which we are going to use is the big endian. That means the most significant bit would be stored at the lowest address in the memory. Let us see the broad features of SRC. As we said, this SRC is basically a RISC machine, which would mean that the length of each instruction is the same, which is 32 bits in this case. So that means all different forms of instructions would occupy 4 bytes or 32 bits. As we have discussed earlier, the interaction between memory and the CPU is from the load store concept. That would ultimately give the ALU unit, the data available in the registers. So therefore, the load store concept is the one which we have already discussed that would apply to our SRC machine. Finally, as a RISC machine, we will limit the addressing modes, making the story much simpler. Let us look at in our next slide on the programmer's model of ISA. Now in this slide, we see the programmer's view of SRC. As discussed earlier, the programmer's view is a programmer who is writing a program in assembly language, or a person who is writing a compiler. The CPU, as we discussed, consists of 32 general purpose registers. We name these registers as R0, R1 up to R31. The two special purpose registers are the program counter PC and IR. These 32 registers and the two special purpose registers, they formulate the central processing unit, which is shown dotted in this slide and has a CPU. On the right side, the main memory is indicated. The memory is byte organized, and the addresses are indicated as 0, 1 up to 2 raised to the power 32 minus 1, which means a total memory space of 4 gigabytes. The notations which we are going to use for SRC are R within square brackets. For example, if we write 3, R3 would mean the contents of general purpose register R3. Similarly, M within square brackets 8 would mean the contents of memory location 8. A memory word at address 8 is defined as the 32 bits at addresses 8, 9, 10, and 11. That would mean the 4 bytes together. The notation further explains the big endian concept, which we said the memory is utilized to store the data. On the left-hand side, we have indicated from the top the address A, then next one is A plus 1, A plus 2, and A plus 3. When we store data, the address A in this example would have the byte M8, next one 9, 10, and 11. So one memory word would consist of the contents of M8 staying at the most significant position, next M9, then M10, and M11, meaning that M8 is concatenated with M9, then M10, and M11. The notation used is we write M8, and with angle brackets we write bit 31 up to 0, indicating that M8 is a data which is 32 bits. However, it is defined as, or it is equivalent to, M8 concatenated with M9, M10, and M11. Please note that big endian simply means that most significant byte in this case, which is M8, is stored at the lowest address, which is in this case A, and the least significant byte is stored at A plus 3, which is now M11, meaning that 4 consecutive bytes in the memory would store one memory word. Next, we are going to look at the structure of the instructions. As we know now that each instruction would consist of 32 bits. The instruction has to convey the information about what operation is to be done, from where to get the operands, and where to store the final data. We classify the total instruction set into 4 formats or 4 categories. In the book, you will note that the number of categories or formats indicated are number 8 or higher. We will consider some of the cases given in the book as a special case of these 4 formats. Let us look at these 4 formats more closely in the next slide. The first information required to be put in the instructions is the opcode. There are 4 different types or formats of the instruction. We call these as type A, B, C, and D. In each case, the length of opcode is 5. Since we need 32 different instructions, 2 raised to power 5, which is 32, we could have different instructions given by a length of 5 bits. So in each case, first 5 bits, the most significant 5 bits from bit number 27 up to 31 would indicate the opcode. In type A, the first 5 bits, bit number 27 to 31, indicate the opcode. Rest of the bits are unused. Why these bits are unused? We have already defined that it is a RISC machine. And by default, each instruction must occupy a length of 32 bits. So therefore, in type A, rest of the bits are unused. That means from 0 to 26, the 27 bits are unused. The assembler could pad these unused bits with zeros. Ultimately, this would mean that after the most significant 5 bits, the rest of the bits do not matter. In type B instruction, we have opcode followed by a placeholder named as RA. This RA would indicate one of the 32 general purpose registers. So that would mean from bit 22 up to bit 26, the 5 bits would indicate the first register, which is designated in this case by RA. RA is a placeholder which would point to and indicate the register, one of the 32-bit registers. Rest of the 22 bits are indicated by a constant C1. So the structure of type B instructions would be that we have one register and one constant indicated by C1. Type C instruction has a structure opcode followed by 2 registers RA and RB. So RA and RB would indicate the position of the one of the 32-bit registers, and an appropriate code would be placed as RA or RB. However, there is one exception, that when RB is 0, this is a special case and it would not mean the register capital R0. After these 2 placeholders, RA and RB, the constant C2 specifies the information regarding an indicator to evaluate the address. Finally, we have type D instruction where opcode followed by 3 registers and a constant C3 would be specified. Let us look at some of the examples of each of these 4 types. type A, we see that there are only two instructions in type A. First one is no operation, and that has an opcode of 0. Now this instruction could be used for idling in the case of pipelining, which we will discuss in a later lecture. Now with opcode 0 and unused bits padded with 0, that would mean a 0 hex would mean a no op in this case. The second instruction of type A is the stop instruction. In this case, the opcode has all bits as 1, which means 31, and rest of the unused bits could be 0. In fact, it's not necessary that we pad them with 0. Whatever is the data in unused bits, it's irrelevant. So important is the opcode. The next type, which is a type B instruction, as we said, the opcode would be followed by a register. We have an example of 3 instructions in this slide, and all of these use relative addressing mode. The first instruction is load relative with mnemonic LDR. It has an opcode of 2, and an example given is LDR is R3, 56. This would be how an assembler or assembly language programmer would write. This means that the memory location given by the contents of program counter plus 56 is transferred to the contents of register R3. The second instruction is load address, and this has an opcode of 6. In this case, we see that the contents of PC plus the constant C1 are stored in or transferred to the register R3. This gives an address location which is relative to PC. It is at a position, in this example, 56 forwarded from the present contents of PC. So this addressing mode is actually PC relative. PC may not be mentioned, and we just call it a relative address. The third instruction, the store one with an opcode of 4, is just the opposite of the load. In load, we move the contents from memory to register, and in this case, we store the contents of a register to a memory location. In this example, the memory location to which we load the contents of R8 is PC, the present contents of PC plus 34. One thing which is quite important and should be noticed at this point is that the effective address is computed at runtime by adding a constant to the PC. When we just assemble a particular program, the contents of program counter may not be defined. When execution is done, during the execution, the contents of program counter would be updated with a figure, for example, relative address, by adding in the first case 56 and in the third case 34. That would give and generate an effective address, and this effective address would be used for storing the data. This is a very important feature, and this makes the program relocatable. That means wherever is the starting point, starting address, and irrespective of that, the program would perform correctly, and the code or the program is called relocatable. Looking at the type C instructions, we have opcode followed by the placeholders to indicate two registers RA and RB and a constant. In this slide, three example instructions are given: load and store instructions, and then later on we have three ALU instructions. The first instruction is load with an opcode of 1. Now we see that load R3, 56. This is a special case which we indicated in the beginning, that if RB field is 0, that would not mean the register R0. So R3, 56 would take the contents of location 56 from the memory and transfer it to the register R3. Whereas in the second instruction of load, it is load R3, 56, and again within brackets R5. Now this R5 is indicated by RB. So RB equal to 0 has a special significance, which does not mean R0. For all other values, it would mean a register. In this example, R5. So what we do, the instruction would be executed in the form of the address 56 plus the contents of R5 would indicate the memory location. So the data is fetched from memory location 56 added with contents of R5, and these contents are placed or transferred to the register R3. Second example of this instruction is LA, which is load address. So LAR 3, 56 is again the case with RB equal to 0. So in this case, the contents of 56 are not picked up. Rather, just 56 is transferred to R3, which is the indicator for the address. Similarly, the next instruction is load address R3, 56, and within brackets R5. Now this R5 indicates the field RB, meaning that add the contents of register 5 to this constant C2, which in this example is 56, and place this address into the register R3. The third instruction, store with an opcode 3, is just the opposite of load. In this case, we place the contents of the register into a memory location. The first example, store R8, 34, is with a placeholder RB value of 0, so the register RB would not be considered as R0. Rather, we just take the contents of register R8, which is RA in this case, and put these contents to memory location 34. And in the next case, the contents of R6 are added to the constant 34, and from R8 the contents are placed or stored to the memory location 34 plus the contents of R6. Next time we'll continue with the other two types of instruction for the SRC. I would suggest that in the meantime you look into more details of what we have learned today. Till next time, Allah Hafiz.